Hi, everyone, and thank you, Juan, for a very kind introduction. It's a privilege to be connecting with you all today. Met some folks at Sci-Fi Latin America in 2019, and I'm thrilled to have this opportunity to reconnect with folks here. So the conference theme is Welcome to a New Dimension, and so this talk is going to explore perhaps a dimension of science, and that's openness. So I wanted to take this chance to explore the role of openness in science, connections between open source software and science, and the processes for collaboration and how we conduct that in open source software, as well as how we do that in scientific research. And as I get started, openness and communities are going to be themes throughout this talk. And I think it's important to begin by acknowledging the people and the communities whose land I'm joining you from today. So where I live currently and where I have the privilege to live and work is it's now known as Vancouver, British Columbia in Canada. But these lands, they are the traditional, ancestral, and unceded territory of the Coast Salish peoples. And that includes the territories of the Musqueam, the Squamish, and the Tsleil-Waututh nations. I also want to say a big thank you to the organizers. This is a world-class event, and I am honored to be able to be a part of it. And so all these folks and everyone else who's been behind the scenes involved in making this all come together deserves a big round of applause from everyone who's had an opportunity to enjoy and get connected throughout this two-day conference. And one thing I would like to do, I'm going to be sharing some of my journey and perspective about projects that I've contributed to or I'm connected with in the geosciences. But I'm hoping that it sparks some ideas of other connections, maybe projects you're excited about, or maybe projects that we could spark new ideas for. And so what I've done is I've created a Google Doc. And I think someone will share it in the Slack channel as well. So if you go ahead and you go to this Google Doc link, I'd invite you to just add your notes, add links, add ideas in English or in Spanish or your language of choice. And hopefully we can build this as kind of a collective resource of ideas that come out of this discussion we have here today. And so we're talking about scientific research. Let's perhaps start by asking what is the definition of science? And so this definition that I've taken here, this is from Wikipedia, which is a community curated resource. And I think that that's kind of a nice way to perhaps start off this discussion. And so the definition here, I'll read it out to you, is science. So from the Latin word scientia, meaning knowledge. It's a systematic enterprise that builds and organizes knowledge in the form of testable explanations and predictions about the universe. And so there's kind of three components to this, and we'll walk through each of these a little bit today. So there's there's what we're doing, and we're building, it's the testable explanations and predictions is the piece there. There's how we're doing that through building and organizing, and there's who is doing that. That's the people and institutions that make up this systematic enterprise. So we're gonna work through that. We'll start by kind of taking a look at an example that really was a paradigm shift in the earth sciences, and this is the theory of plate tectonics. And so this might have been something that you were taught as a part of early in an early science education, but the idea is actually although the idea has been around for quite a while, the evidence and sort of proof and wide acceptance of this within the scientific community was actually relatively recent. But the idea itself dates back centuries at this point. So there was observations as early as the 1950s by a Dutch map maker that the Americas looked as though they were torn away from Europe and Africa, perhaps by earthquakes and floods. So it was observed that the continents kind of look like puzzle pieces that seem to fit together. And so although this idea has kind of been in the air perhaps for centuries, it's not until 1912 that a theory started to develop. And this original theory was proposed by Alfred Wegener, and it's called continental drift. So this idea that somehow, we don't necessarily know the mechanism, but somehow the continents have moved around. And so he proposed the Pangea supercontinent. So all of these continents were once together and subsequently broke up. And one of the key pieces of evidence that he pointed to was fossils. So both sort of this fit of the coastlines that had been observed for a while, but also fossil assemblages. And so there were similar fossil assemblages noticed, for example, in South America and Africa. So now, very far apart. But if we look sort of at this puzzle piece fitting together, those would line up. And so this was one of the pieces of evidence that he used, but at the time this was not widely accepted by the scientific community. And so this was one piece of evidence, but there's additional pieces of evidence that we're starting to build after Alfred Wegener proposed this. And so some of this evidence is geophysical evidence. And so this is the domain of science that I primarily work in, is working with geophysical data. And so what these data are is we measure data over the surface of the Earth that are sensitive to physical properties in the subsurface. So for example, we've got some sort of source that's going to input energy into the Earth. And so if we're looking at magnetics, the Earth's magnetic field is actually our natural source that we're using. There's other experiments that use controlled sources. But in this case, with magnetics, the Earth's field is our source. And that interacts with magnetic materials in the subsurface. Then we can measure magnetic field data over the surface of the Earth, and from that gain insights about what actually is in the subsurface. So let's look at a few of the pieces of evidence that came to be with respect to plate tectonics. So in the 1950s and 60s, there's a fair bit of geophysical evidence that people were starting to put together. So there's the location of earthquakes. That's that top image there that you can see. So the way that those were found out and mapped is that there's seismometers around the world, and these measure the motion of the surface of the Earth. So when there's an earthquake, we can measure the motion around the world, and from that, compute basically where those earthquakes actually happened. And you start to see that there's patterns with that. These are not just randomly anywhere in the world. There's actually a fairly high density. You can see actually in the middle of the map, and that area is now known as the Pacific Ring of Fire. So we know there's a lot of tectonic activity in this region. There's also gravity measurements that were made at mid-ocean ridges, and this starts to give evidence of very dense mantle material coming closer to the surface. So gravity is sensitive to the distribution of dense material in the subsurface. One of the very strong pieces of evidence was magnetic data. And so with measurements made by magnetometers that were actually repurposed from World War II, originally magnetometers, or these magnetometers were used to try and locate submarines, but they were repurposed to map out the ocean floor and give magnetic field measurements over that. And what scientists noticed is that there's this pattern of positives and negatives that are parallel to these mid-ocean ridges. And now what we understand of that is that that's the impact of the plates spreading. So these plates are spreading apart. We have hot magma material coming up to the surface. And what happens when it comes up is it actually cools, and there's magnetic material in there, and that magnetic material basically freezes and locks in the direction of the Earth's magnetic field at that point in time. We also know that the Earth's magnetic field changes through time, and so that's what this striping has happened. At one point in time, the plates are spreading apart and the field is going in one direction. The field changes direction, and as as these plates continue to spread apart, the magnetic field that's going to be frozen in is in the different direction. And so it gives these complex striping patterns. So again, this is another piece of evidence kind of building up this and giving more weight to the idea that the continents have moved. One piece of computational evidence that I think is quite interesting is this map is known as the Bullard fit. And so what they did in this paper is actually posed this puzzle piece problem as a computational problem. And so what they looked at is they posed an optimization problem where you try and minimize the distance and the overlap between the different continents. And this was seen as a very strong evidence point for plate tectonics. It took this this qualitative observation that, it looks like we have puzzle pieces that may fit together, and made it quantitative. So this was seen as a significant evidence point. So at this point, I've shown you lots of examples that start to perhaps fit together the idea that the continents have moved. But there's still a big lingering question, and that's what's happening. How are the continents moving? How is so much mass being moved around the world? And so what we now know is that this is mantle convection. And so in an early paper by Turcotte and Oxberg, they posed and explored the idea of seafloor spreading. They developed a mathematical model and they did a mathematical analysis to understand the different components. So at the top, there's this cold boundary layer, that's the crust. Beneath that, we have the hot magma. They looked at pieces of data such as the spreading rates from magnetic data and thermal data along the ocean floor. So they worked with this mathematical model as well as all of this evidence to develop a model of seafloor spreading. And so this demonstrated these ideas that, okay, we do actually have magma that's coming up at these mid-ocean ridges and spreading the plates apart. But then the question that raises is, okay, if we've got something growing, we know that the Earth is finite, and so what's happening on the other side? How is this mass actually conserved? So there are a number of different ideas that were proposed. There's one example of a shallow mantle convection, perhaps. So maybe these plates are going to sink down at the other side, and there'll be this thin layer that comes back up, and it kind of recycles. Maybe we've got something like a bit of a conveyor belt. And to test out these ideas, another mathematical model was developed. And so this work was done by Schubert and Turcotte. And I took a screenshot of the equation that they worked with. And so you can see that this is a pretty complex equation. It takes into account pressure, density, velocity, viscosity. So there's a whole bunch of different components that they've brought in to build up this complicated nonlinear partial differential equation. And so in order to gain insights about that and to actually sort of test out this model and see what it might provide in terms of insights of convection, they needed computation. And so this was an early example of sort of the impacts. They developed this one-dimensional model and programmed that up and actually ran computations to examine it. And so what they were able to show through this mathematical and computational modeling is that in order to agree with all of the available evidence, so with heat flow, with gravity data, and also to produce something that was physically reasonable, required this model of whole mantle convection. So it's not that we've got this little sort of conveyor belt of material coming back up, but it's that the whole mantle is actually involved in convection. And so with all of this evidence, and now with actually a physical mechanism proposed for how plate tectonics, how the plates are actually moving, this really was a paradigm shift in the way that Earth's, in the thinking about our Earth and in the theories we have to understand it. And I think this is a really nice example because it is kind of the process of science is building up evidence. There was no single piece of evidence that was a smoking gun and was enough to convince everyone. But what we needed was evidence across a suite of different disciplines. So from geology and paleontology, looking at fossils, also with magnetism, looking at the magnetic fields, looking at earthquakes and other geophysical data. And so the people who needed to be involved in that come from a very diverse set of backgrounds, different computational abilities, different methods of analysis and skill sets. And also computation played an important role in sort of two particular examples that I highlighted. So in this puzzle piece fitting of the continent, to quantify a qualitative observation, provided much to strengthen that evidence point, but also to model and to test theories. Is to be able to develop a mathematical model and be able to explore different scenarios. So it played an important role in both of these components. So since then, what's changed? What's new? There's a number of things, but a first couple of things to point out is now the availability of data. We've got sensor networks all over the world. We have satellites circling the globe that are providing us and streaming so much data, so much high quality data for us. This image on the left is Grace is the name of the satellite. It's a gravity satellite, it circles the globe and provides high quality gravity measurements over the surface of the Earth. There's a lot of fascinating things in this picture, and I could talk for a little while about that. You can see things like the Mid-Atlantic Ridge. There's a bit of a gravity high there. There's lots to unpack, but it's pretty incredible, the data that we have access to. And also the change in computational abilities. So that example that I showed you of the 1D convection model, that was in 1972. To give you some context for where computing was at that point in time. That's the same year that the game Pong was released, and it's a year before Intel released its first microprocessor. And if you think about what we have access to today with cloud computing, we essentially have access to unlimited computation. And this image here shows a complex model now of understanding the liquid core of the Earth. So looking at dynamo theory and how that actually generates a magnetic field. So this is a very complicated computational fluid dynamics problem that needs to be solved. And those are tractable at this point in time, which is pretty incredible. So I want to take a look at a current use of geophysics and sort of a current example of the use of geophysics for a problem that is quite timely and relevant around the world, and that's looking at groundwater. So in a lot of places, water resources are somewhat scarce, and especially as the climate is continuing to change and as populations continue to grow, surface access to fresh water is often stressed in quite a number of areas. And so that motivates the need to look for groundwater. So if we've got porous rocks like sandstones, in between those grains, we actually can have fresh water that's stored there. And actually 97% of all available liquid fresh water on the Earth is underground. And so there's motivation to be able to locate that, but also to properly manage these aquifers to ensure that we do actually have them as a sustainable resource. And so again, geophysics can play a role here. In this case, the primary physical property that we're interested in is electrical conductivity. So looking at the difference between perhaps a water saturated sand, which will be relatively resistive, and a clay, which will be relatively conductive. That's what we're sensitive to if we look at electromagnetic experiments. And in particular, airborne electromagnetics is an important method that we have access to, because from this helicopter, we can fly a helicopter and collect data at about 100 kilometers an hour. And so we've got a helicopter, it's going to tow a loop, and we put a current through that loop. That generates a magnetic field. That magnetic field interacts with the conductive earth, generating secondary currents. And those currents produce their own magnetic fields. So that's the data that we acquire. And so from those data, what we want to be able to do is actually estimate a subsurface model of the resistivity of the Earth. And so that's what this image on the right shows you. And so you can see there's a few different features. Some of the red regions are perhaps sand regions, and this is where we might expect there to be aquifers. You can start to ask some important questions like which aquifers might be connected and which are disconnected. That's going to change how you regulate the pumping that might be allowed in a given region. So the data in the image that I show you on the right, the way that was actually produced is from each of those, each location where we've got a measurement of the magnetic field from this helicopter. We've run something called an inversion, and that's an optimization problem where we're trying to work with Maxwell's equations and estimate a conductivity model of the subsurface that's consistent with those equations and those data, as well as maybe any geologic assumptions we have or geologic knowledge about the area. It's a massively parallel problem. Each of those sort of logs that you see, we can run those in parallel. And so, as with many fields in geophysics, computation is now a core sort of daily part of our research. And this example comes from the Central Valley in California. This was provided to me by Soggy Kang, and this was work that is done with Rosemary Knight's research group at Stanford University. And so where this project is going is really exciting, is they're actually working on flying airborne electromagnetics over most of the Central Valley in California. And this is important because the Central Valley produces 25% of the US's food, using less than 1% of the nation's farmland. but it is under significant water stress, and so they do need to figure out what are regulations that can be put in place to sustainably manage these aquifers. And so this is again an example of research that requires multiple disciplines. So yes, geophysics and developing a 3D image of the subsurface is one component, but you need to have an understanding of the geology, bring in knowledge there, and also be working with folks in the water board, in local communities, with regulators. And so it's, you know, an example of where research intersects with society. And so I think what both of these challenges, or what both of these examples show, is, you know, fundamental changes in the mindset and the thinking of a community, and big challenges that intersect with society. These are iterative. It's an iterative process to make progress. It requires multiple disciplines, and it requires involvement of multiple stakeholders. These, especially when we talk about, you know, scientific problems that intersect society, as so many do. Being able to communicate research and being able to bring in voices from these different domains is so important. And so I think what perhaps the questions we might ask ourselves in looking at these and seeing that these are important components of solving these big problems is, how do we make these iterations, this iterative nature of science, how do we maybe make that faster, to speed that up, make it more efficient? You know, the process of you know, transitioning from the idea of continental drift to now actually having a whole mantle convection theory of plate tectonics, that took decades. How do we include a more diverse spectrum of voices? We need ideas coming from different disciplines, from folks with different backgrounds, different cultures. And how do we broaden collaborative circles? You know, the papers that we look at in the example as plate tectonics evolved is, you know, 1 to 3 authors is kind of typically who's involved in each piece of the project. What can we do to broaden those circles? And so I think, you know, software plays a really important component of accelerating science, both because these are tools that we rely on. So the numerical simulations, optimization, being able to actually explore large data sets, software is a critical piece. But also to capture, document, and share what's been done, is to be able to now share scripts, share notebooks, and things like that, that demonstrate the work that you've done, enable others to build upon that. And this is where the Python ecosystem plays such an important role. And what I think is also so important here is that word ecosystem. When we think about working with tools in the Python world, is that it is this collection of interoperable tools. And by working in this modular way, we keep problems scoped. So Dask is working on parallel computation, and in SimPeg we're working on geophysics, and in PyVista working on 3D visualization. But these pieces, they fit together, and improvements in any single one of them can have very broad impact. And so it's both the software as a tool, but also this way of working that I think are important components as we think about how the process of science and what it is we're achieving. And within this, I specifically want to highlight the role of Jupyter. In science, notebooks play a really important role in accessing computation. So being able to, you know, transition from working perhaps in Excel to having something that has more computational power behind it. The notebook is a really important tool for making computation and making programming accessible. And for reaching broad audiences, the notebook is something that you can share your narrative, build up interactive components, and actually have that reach a broad audience. It facilitates the interactive sort of iterative workflow. And so when you talk about sort of yourself as a researcher exploring a single data set, you know, having this conversation between you and the computer, and so much of this language that I'm using comes from perhaps the original grants and original ideas around the IPython notebook and the Jupyter community. It's also a powerful tool for discussion with others. I've used this in teaching contexts and in research contexts. Because you actually have access to a live computational environment and kind of use the notebook basically as a tool to facilitate discussion. So if somebody asks a question, you can update some parameters and actually visualize those results. And so this space of kind of having and enabling computational conversations is a really important advancement. And with that, resources for being able to actually widely share this. So Jupyter Book is a great example of how it's possible to take work that's been done in notebooks and publish those actually as a collection that you can share with others and make that actually discoverable. So, you know, being able to actually share research, share knowledge without having to be a web developer, but share that computational content opens that up both for folks to be able to consume that information, but also for researchers who aren't necessarily familiar with web development, how to deploy a website. It makes it possible for them to be able to share their knowledge as well. So the other component that we talked about, you know, we talked about what we're building in science, and these are testable predictions and predictions about the universe. And so what do we mean by testable? And so reproducibility and replicability are two words that come to mind and are certainly a very important part of the conversation of science right now. On the right, I've put in an image of the National Academy's report that was put out in 2019. And it's a great example and really highlights the importance of open source software and open science practices in reproducibility and replicability. So what do I mean by that? There's kind of two levels. We often think of the first level of using the same data and tools. So being able to pick up a notebook that I created and have somebody actually be able to go ahead and run that and get exactly the same results. There's another level, which is actually using perhaps different data or maybe some different tools, different methods. And this starts to speak to being able to actually extend it and build upon somebody else's work. And I think one thing that's important to notice is that progress in being able to share your data, your tools, your workflow, and have somebody else just be able to hit the run button and get the same results is a very important step towards others being able to actually extend, build upon, and try out methods with new data. And I've put in a few logos of different initiatives or acronyms you may have seen with respect to open access. So yes, we have open source software, but there's a lot more progress being made with respect to opening up data sets and sharing preprints. And so preprints are, you know, you've got your paper that we're going to submit to a journal, but preprint servers, what they let you do is actually publish that openly. And that's so important because the papers are actually, you know, the methods, you've captured some of the storyline, you're thinking about the problem in a paper. So having access to that story, as well as the data and the computational steps that were taken are all important components to being able to actually share work and have that be easily reproducible by others. Another important project in this space that I think has really driven the adoption of standards for computational reproducibility is Binder, as the Binder project. And so, in a sense, Docker is a standard for a reproducible environment. That's something this community, I'm sure, is somewhat familiar with. But for the general scientists, myself included, you know, getting up and running with Docker is a lot to learn. And so this is where repo to Docker has played an important role of being able to go from standard files that the community uses, so in Python and environment.yaml or requirements.txt, and actually build that Docker environment. And so this has been an important step for making that more accessible. But the fact that Binder actually enacts this and pieces it all together, there's motivation to actually get your scientific work into a state that it can be reproduced by others, because you can send them a link. Somebody else can actually go ahead and start running your work and playing around with it. And so I think Binder's been an important driver in the adoption of standards for computational reproducibility. Now, if we talk about this second point of different data and possibly different tools, I think it points towards, you know, extensibility and generalizability. And this is something we talk about in software if we're wanting others to be able to actually use and build upon our work. And testing is such an important component of that. And there's a few different levels of testing. There's things that we might know in science or in software, for example, mathematical properties. There's simple things that we know our code should satisfy or our ideas should satisfy. Those things we can test out and we can be relatively confident in. But often that subset of things that we really know we can prove is relatively small compared to what it is that we are actually trying to build. And so coming up and examining simplified solutions. So often if we talk about physics, there's lots of solutions for spheres in half spaces or full spaces. So it's a relatively simple, but still slightly more complex setting where we can build up, start to build confidence. But as we go beyond that, as we go to complicated models and complex ideas, if you think about, big deep learning problems and things like that, these are complex. And there's not necessarily going to be a simple solution that we can compare to. So there are some things we can do. We can compare with other code bases. And so that shows the importance of having other open source software packages and other flavors of implementations out there. If you can compare between sort of two independently developed solutions, that builds confidence that what you've done is correct. But also the fact within, in the open source community, if there are others who are actually using the software, trying it out on their own data, on their own ideas, folks are going to test things out and encounter the limits, and that's perhaps where they might either note that that's something that this is the boundary of what we can do with this software, or perhaps it's something that they could actually go in and extend and update some of those assumptions later on. And so this role of a community actually in the testing framework and in the space where we can actually extend and generalize ideas is very important. So that covered a bit of testable explanations and predictions. So now I want to move on to and look at a bit of process, the second part. How do we build and organize? How do we build and organize software, and what does it look like in science? So if we ask that question in software, we've got a bit of a hierarchy of the way that we organize the components, right? You might start with a script, sketch out some ideas, refactor that into functions that are reusable, and perhaps even go to the next levels of developing a class or a module and maybe distribute something as a software package. And so each of these are at a different sort of level of organization and getting from a script to a software package. The process that we use is refactoring. And so got in the bottom this little circular diagram where we've got the tool that we're working on and the community of people who are working on that tool. And it is circular in a sense, because what it is that we're doing is we're always working on actually that same repository, for example, or maybe eventually it ends up splitting into multiple repositories, but we're working on sort of one common set of tools. We're iterating on one common set of tools. And in doing so, we can enable others to reuse that. We might do things like improve efficiency, simplify some of our ideas, or make them more testable. But all of these components, and as we kind of continue to work on and have others, exploring and also iterating on this code base, what we really get towards is something that is more extensible. Is that when there are more people using it, contributing their ideas, running into roadblocks and fixing them, what that does is it extends where these components can be used. And so what does this process look like in science? There's also a bit of a hierarchy. And so we can think about, as you're building up ideas, you might give some presentations and talks, try and facilitate some conversations around them, conference abstracts and publications. But this iterative process, when we looked at software where we're iterating in place kind of on one thing, this really tends to be in the scientific space, a very small circle. Is your collaborators, right? Is those two people you're going to write the paper with. That's who you iterate with. And then at some point in time, you get that paper out, send that out to others, and you might perhaps get some critiques and things like that. And maybe somebody else even writes a paper citing yours, and they have some critiques or new ideas that they're building upon. But in a sense, it's this divergent process, right? Those critiques or new ideas, they don't circle back into the original. And so we don't kind of have necessarily the same tight circle with refactoring. We've got a much more diverging sort of pattern. And I think that kind of asks the question is what are we perhaps missing by having this diverging pattern of the development of knowledge? And so with respect to practices of open science, the fact that more folks are making data available, openly licensing papers, openly licensing data sets, posting them and making them findable. And these are all sort of steps we're making progress towards people being able to reuse and build upon work that's done. But I think there's also some significant challenges, is we don't really have necessarily, the tools for collaboration really at these larger scales are still challenging to use. There's some places where Git and GitHub are a great tool in computational work, but it's not necessarily the right tool and not necessarily a tool that all scientists are familiar with. And so if that's adopted as the tool for collaboration, there's people that we're perhaps missing. And within sort of software, we've got, mechanisms for importing functions, importing packages, and really reusing on a very granular level other people's work and remixing it with our own. But in science, we don't necessarily have the same mechanisms or really the same culture of reuse that's yet been established. Yes, there is content that's openly licensed that is available. But copy and pasting from one place to another is viewed as plagiarism, and in some cases it is plagiarism. But there's spaces where I think it'd be an interesting question to ask: is what does importing an idea actually look like in science, and what are mechanisms where we can reuse and remix content, and how do we do that appropriately? And so that's something that I don't think the scientific community has yet really figured out. Don't have the answers, but it's something that's interesting perhaps to explore. I do though think that there is more of a pattern in culture of reuse in educational content. And so one project that I've been privileged to be involved in is the GeoSci project. And so this is a collaborative effort to develop open content for geophysics education. So we've developed a number of textbook-like resources using a lot of tools in the open Python ecosystem. And it's been adopted by instructors at a number of different institutions and universities around the world. And it's been exciting to see that we've also received contributions back from them, is that we've tried to build this project up in a way where it makes more sense and there's incentives to sort of bring back ideas, simple things like typo fixes into one place. And we're certainly not the only example of open educational content. There's many others, and I would love to see what people put in the document for ideas there. And so I think education is a space where we're perhaps progressing a bit more rapidly with the ideas of reusing and remixing content. And a lot of these ideas and questions are motivating the development of CurveNote, which is a project I'm excited to be involved in, and Rowan and Steve are really leading the way here. And so a lot of the ideas here to bring in things we've learned from open source software development and adapt and see how they apply to scientific writing. So things like versioning and licensing content are so core to how we're actually able to reuse software. And similarly, scientific content. But also recognizing that, Git and GitHub are not necessarily the right place to be, or are not necessarily well suited for the types of documents that we work with in science. The narratives and the data and Jupyter notebooks that we work with, the model of collaboration is perhaps a bit different. And so that's something that we're exploring there. And so a lot of the current geosci development is happening in CurveNote, and quite excited to just continue exploring what perhaps a model of scientific content development looks like when we take in some of these practices from open source software and try and adapt them to writing and collaborating in science. So another important component of the process of science is peer review. And so I've put the words collaboration and peer review in here. And what I think is interesting in science, these are treated very much as two distinct phases. As I mentioned, we've got our collaborators that are in our tight circle, and these are going to be the folks that are on our paper. And peer review is a very distinct group of people that sent out the paper sent out once it's ready, and they're sort of viewed as two distinct phases. But when we look at this process in software, these intersect very tightly. Is that if we look at a pull request, that is both a collaborative process and a peer review process all in one place. Is that somebody from the community has got some ideas for improvements or bug fixes or extensions of a project. They ask permission to bring in those changes, and somebody who's familiar with the project is then going to provide feedback and ideas and perhaps ask some clarifying questions and things like this. And so, in a sense, this review process is still very collaborative. Everyone in that space is working towards one goal, which is improving this software package. And so I think in science, there's good reasons to ask for independent reviews and independent ideas or an arm's length assessment of something. But I think maybe we're missing opportunities to improve and incorporate ideas that happen when you have these tighter circles of collaboration. And I think some interesting data points and examples that are trying to sort of turn this very distinct process of collaboration and peer review into perhaps something that's a little closer together is the Journal of Open Source Software and PyOpenSci projects. And so in both, peer review of scientific software is a really important component. And I think it's really interesting to see that you get comments like this, that the review process was straightforward and even fun. That's not something that you'll hear many scientists say about the review process for their paper. And in many cases with JOS and PyOpenSci, I think one of the evidence points that I'm really excited about is the fact that often it is the case that actually some of the reviewers do generate pull requests and make suggestions to the software package, that in the process of reviewing, they become collaborators. And so I think that that's an encouraging points of evidence, and perhaps something we should try and learn more from in the scientific community. All right, so I want to look now at the third part of this definition. So looking at the systematic enterprise, and what do we mean by that? So in academia, we often think about, the people being professors and graduate students, and the institutions being universities. But as we've seen, modern science intersects industry, the public sector, the journals we publish in, national labs. It's a collaborative space, and there's the problems that we're tackling need input from each of these different communities and people from these different backgrounds and with different interests. And if we look at open source software, I think this is a good example of where the lines are very fluid. Is that, if you look at a project like Jupyter, there's folks who are contributing from industry, there's folks who are contributing from universities, motivated by education, from nonprofit sector. And so these multi-stakeholder projects involve people and institutions very fluidly. And I think as we're shifting towards a more open model of science, we're starting to see similar shifts happening, where people are collaborating from different institutions, and also sort of different sectors, even with industry, with nonprofits. And so there was a nice example and nice discussion of this in the paper that was recently published by Brian Granger and Fernando Perez in Computing in Science and Engineering this year. And they discussed three aspects of Jupyter. So the interactive computing component that we discussed earlier, the sharing of computational narratives, but also the idea that Jupyter is more than software, that it is these communities. And they specifically highlight these ideas of a community of practice. And so that being defined as a group of people that's motivated by a common problem set or common interests that develop community accepted practices within that community, often with the goal of advancing a field or a particular domain or tackling a challenge. And so one example, or a couple examples here, includes in the earth sciences, include the PanGeo and the Jupyter Meets the Earth projects. And they've got a common anchor in software for geoscience research. So investing in the ecosystem of tools, investing in tools like Jupyter, Dask, Xarray, ZAR, that are all at this point core to working with large geoscience data sets. And with that, there are community principles such as contributing to the core tools, contributing upstream to projects that are supporting your research. And so I've included a couple links here where you can check out and examine some of the resources that these groups are developing. Another project, a nonprofit that I'm really excited to have the privilege of being involved in is 2I2C, the International Interactive Computing Collaboration. And so it's an organization that has grown out of initiatives including Pangeo, the Berkeley Data Hub that's supporting undergraduate education across the Berkeley campus, as well as projects for interactive computing in Canada. Callisto serves students in grades 5 to 12 across the country, and Syzygy serves universities. And so in all of these examples, interactive computing is sort of a common grounding point for education and different disciplines. And so with 2I2C, a lot of the mission is to deploy and manage interactive computing infrastructure to support these different communities in research and education. There's many other examples of communities of practice, including groups that have been mentioned at this conference, PyLadies Colombia, Django Girls, and many others. But two others in the geosciences that I've been inspired by are the Software Underground, which is a group of people who are motivated to solve problems in the geosciences, and it's really kind of grounded in sharing information and ideas. And Slack is actually a sort of a core tool that this community uses for communicating and sharing knowledge and ideas. And out of that has grown a lot of opportunities for peer learning, workshops, hackathons, and things like that. Another community that's connected is GeoLatinas. And their mission is to embrace, empower, and inspire Latinas to pursue and thrive in earth science careers. And there's a number of initiatives that this community this community is working on, including things connected with professional development. One connection point I wanted to highlight specifically for folks here is there's a coding group. And so if you're interested in connections with coding problems in the earth sciences, I would encourage you to take a look. And these communities have a really important role in bringing people together, connecting people interested in working together to solve common problems, and developing the mechanisms to communicate and connect people. And conferences like this are a great example of the important role that organizations play in bringing people together. And so I want to just take a step back and we perhaps revisit, what is this new dimension of science? We face some really important hard problems right now in science: climate change, managing natural resources, and many others. But it's also a really exciting time. Openness is changing how science is being done. We have these large, fascinating, exciting data sets, and the software that folks here are working on are such an important part of being able to actually gain insights from those data and solve problems. And this includes domain-specific tools. Yes, I work on some tools in geophysics, but also general tools that support the ecosystem, both in scientific computing, but also for projects that make it easier for us to communicate, share results, deploy websites, be able to share knowledge. These are all important components for driving science forward. But another thing that's changing is how we connect and share information. These examples that I showed you early on with plate tectonics, we're looking at author groups of 2-3 people is quite common. These small collaborative tight cohorts. But now, as we're looking at fundamental discoveries that are happening right now, this recent paper on the discovery of gravitational waves, this was with 1,255 authors were included in this paper. This large collaborative network is what's required to tackle very hard problems. And it's a fascinating thing to see a paper that, there's 8 pages of scientific content and the author list plus affiliation is 7 pages. to almost equal weight in sort of what is being said and who is actually saying it. And it just simply wasn't possible, 40 years ago to have a collaborative network that's that large, but now it is. And so we're able to sort of take advantage and what else can we do when we can bring together the ideas, backgrounds, and knowledge from such a large group of people. And in software, I think that these networks, we see that they can actually be a magnitude and orders of magnitude larger. So within SIMPEG, one of the projects I work on in geophysics, there's 19 people who have directly contributed to SIMPEG, but we're standing on the work and the shoulders of 24,000 others. And that's so exciting to be able to see, is that, this large collaborative network, and many of whom I certainly don't know most of those 24,000 people, but we're able to actually collaborate and connect in this ecosystem that we participate in. And some of this is true in science too. We are standing upon the work that has been developed and the knowledge that's been developed before us. But it still is somewhat in this linear diverging fashion, is that we cite the work that was previously done, but what sorts of things can we do to actually iterate on ideas in place, and how do we broaden who we're iterating and who we're collaborating with? So as I said, solving hard problems and making impactful changes requires input, ideas, knowledge from diverse communities with different focuses, different skill sets, different interests, different cultures, backgrounds. These are all required to actually be able to make progress on hard things. And the way that we work in the open Python community, I think, is making substantial contributions to the expansion of openness in science. Both, with respect to tools that are being developed for scientific computing, for tools for disseminating content, but also the tools and practices for widespread collaboration and building these large collaborative networks. And so we're making a lot of progress, and I think this community has a really important role to play, and there's still lots to do. And so with that, I will say thank you and leave some contact information here. Love to hear from anyone if this has sparked ideas, if you have critiques, if you got criticisms, questions, I'd be delighted to be in touch. And I want to give a special thanks to Rowan, Soggy, and Doug, each of whom took some time to work through this presentation with me and share their ideas and thoughts along the way too. And so with that, I'm happy to take any questions if that's something we can do here.